Hey everyone and welcome back to my channel. So today I'm again back with another interesting question on switch capacitors. So if you haven't already, please do watch the part 1 and part 2 of switch capacitors so that you will be able to solve these questions more and more quickly. Also, we have launched our placement courses, that is analog VLSI cohort 0 to 100 and also our digital design placement courses. So those courses you can check out on our website preffusion.in, and also we've launched our full course for GATE Titans batch for both electrical engineering and electronics and communication engineering. So all those things you can check out on our website, that is preffusion.in. So let's get started with the question. So here I have basically many circuits, right? Okay, and this switch phi is actually closed at t equals to 0. So switch, I will write here, switch is closed, switch phi closed at t equals to 0. So if I close it at t equals to 0, so what will be the voltage at the node X? Can you tell me the steady state voltage at node X? Okay, so this is all, like these are the 6 circuits and this is the extra 7th circuit. Okay, so try to pause the video, try to solve it by yourself, then you see my solution. How do I solve it? So let's start with this first circuit. So the first circuit is actually the most interesting one. May seem most simple, but actually is the most interesting one. So here, what is happening is that if I copy and paste the circuit over here, and before the switch is closed, right, I have to, obviously in case of transient, right, you have to see the states of the elements, energy storing elements, before any change has been happened. Okay, that also you have to take care of. So here, before the switch has been closed, can charge be transferred anywhere, any place? So charge cannot flow from here, right? Because this switch is open. No charge can flow here. Again, this node, right, is actually floating. This capacitor is actually floating. So can any charge flow? No, right? It needs a closed path. It needs a closed path. So no charge can flow through this bottom capacitor, and obviously no charge can flow to this capacitor. So obviously no charge is flowing. So whatever states are there, that will remain as it is. Almost at t equals to 0. Then at t equals to 0, what will happen? I will close the switch. So if I close the switch, I will just copy the circuit. If I just close the switch, what will happen? Switch is closed. Now obviously I can clearly observe that, okay, this plus is also gone. Some charge will flow. Why some charge will flow? Because this is higher potential, this is lower potential. Okay, so obviously charge should flow technically from the higher potential to lower potential to make this voltages potentials same, right? Okay, that's why, because they are almost in parallel, just like that. So how will the charge flow? So you what equation you write? You write that simple equation, right? That like initial charge was what, CV plus 2CV, final charge is what, 2C into VC. So VC will be 3 by 2 V, right? And from that you will be able to find 3 by 2 V. Very simple. Well, okay, that is very good. That method is very good. That method will work for the first few questions, but for the later questions, right, that method will be actually very difficult to execute. That also I will explain. So I will solve with basic method. If you already don't know about that, I have taught in my part 1 of switch capacitors. You can go there and watch that. I will link like all the parts to the videos in the comments below. So here, what I will do is, I will assume that, okay, charge is flowing out from this higher potential to lower potential. So I will assume that some charge X will leave from this positive plate, right, and will come to this negative plate. Okay, so charge will leave. So this will be minus X, this will be plus X, and as throughout the whole capacitor, right, throughout the two plates, overall charge should be 0. Some of our overall charge should be 0. So if this is plus X, right, this will be minus X. Okay. Now one more thing is that what was the initial charge that was present in this plate? The initial charge was C times V at the top plate, right? So this is CV, and here it should be minus CV, and here what was the initial charge? It is plus 2CV, and here it is, this should be plus X and this should be minus 2CV. Okay, so these are the charges basically. So now what I can do is I can use the same thing. I will name this node as A right now. I will name this node as A, and here, right, I actually cannot define the potential here with respect to ground because they haven't provided me any ground. Okay, so you have to understand they haven't provided you any ground. So in the interview, if they don't provide you any ground, you ask the interviewer, can I assume any reference? Do you have any preference for choosing the reference? If they give you the preference, obviously you can choose it by yourself. If they don't, then you have to go by them. So currently no ground is given. I will not choose any ground here. Okay, I will not put any reference here. So then how can I define this potential? Now I cannot define the potential at a node right now. I have to find out the potential with respect to some other point. So I will find V, this node will be A. Okay, so I will find VAX. I will find VAX. Okay, so because this X is common between both these two capacitors, and another thing that I notice is whatever charge that is flowing out of this capacitor, right, actually it is totally coming to this capacitor, not going into this capacitor. Why it can't go to this capacitor? Because if some charge goes to this capacitor, right, it needs to flow back, right? It needs a path, closed path, but this actually doesn't have any closed path. This is floating, so obviously no charge will flow here. Okay, so what is the initial voltage? If nothing is given, this is the zero voltage, right? So this will actually remain in zero voltage. Okay, we'll talk about that later on. So first of all, let us find out this VAX potential. So how can I write this VAX potential? I can write this in two ways. What are the two ways? First of all, this potential difference and this potential difference. So what is the potential? How can I write the potential? You know, Q is equals to CV. So what will be V? V will be equals to Q by C. So total charge on the top plate divided by the capacitance of the capacitor. So what is the total charge here? Total charge is minus X plus 2CV. So total charge is minus X plus 2CV divided by the capacitance. This should be equals to what? This, right? So here what is the total charge? Total charge is CV plus X. Then again I will divide by the capacitance. So if this is CV by X plus X divided by the total capacitance. So now I can equate these two, right? And from equating these two, I will be able to simply find out my X charge. So what will be X? So here, this is not that X, okay? Not that X. So this will be 2X. If you know, you know. So this will be 2X and this will be minus 3CV. Am I correct here? This is 2, no, not minus 3CV, sorry for that. This will be plus CV, right? Yeah, plus CV. So my X will be CV by 2. X will be equals to CV by 2. And now if I want to find out this potential across this capacitor, final potential, right? What is the potential? It is simply Vx. What is the Vx? Either this or this. So if it is CV by 2, this will be 3V by 2. Okay, Vx will be 3V by 2, and if you would have used that equation as well, that is C times V plus 2C times V initial charge should be equals to final charge equals to 2C, because these two gaps are in parallel, into V common. So V common will come out to be 3V by 2. Same result. Okay, but the main question what I asked was the potential at node X. What is the potential at node X? So you don't have to do all this business, right? Funny business, because main potential across the X actually is undefined. Okay, why is it undefined? Because this node is actually floating, and I don't have any reference point or ground to define this node. Okay, basically I cannot define this node voltage as well, VA, right? I cannot find out this node voltage because there is no reference here, no ground with respect to whom I actually find out voltage, because voltage is actually generally find out with respect to 2 points, potential difference, if you remember. That's why the name potential difference. But whenever you are finding the potential at a node, basically you are finding that potential difference with respect to the ground. Okay, another point is actually ground. Okay. So that is the important point here. No ground is given, so actually none of the voltages, right, are defined. I can find the voltage across these 2 points, that is 3V by 2, but I cannot exactly say what is the voltage at point X or at point A. So that is one important point. And this capacitor will remain at 0 voltage. Okay, no charge transfer will happen. So for the first one, right, it is undefined. Let's solve for the next one. So if I go and solve for the next one will be a bit simple, because here they have given us a ground here. So that will be a bit simpler. So if I see this, now I will use the same equation that before, right? Before closing the switch, can any charge transfer happen to this capacitor? Because now there is a ground here as well. Okay, there is a ground. So if some charge transfer have to happen through this, right, it needs a path back. How will it go back to this point? This doesn't have any path back. So before closing the switch, actually no charge transfer takes place, because okay, fine, some charge is coming here, some X charge is coming here, it is outgoing, but from here how will it go back to this point, right? it doesn't have any path back, so it can't go back to this point. So no charge transfer will be happening before t equals to 0. So at t equals to 0, again the switch has been closed. So this time the switch has been closed. So if the switch has been closed, okay, so this, right? So basically again I can use the same formula. Okay, this analysis will remain same because this is the VA and VAX, like whatever happens to X, I don't care, but this VAX will remain same, because why? Again some X amount of charge will be flowing out from this 2 volt capacitor, 2V capacitor, and that same X amount will actually come in here, okay, and it will come from here, right? So basically no charge transfer is taking to this bottom capacitor. So again the same thing, exact ditto, same equations. My X will be CV by 2, okay, my X will be CV by 2, and what will be my VA, what will be my VX this time, right? This ground is defined. So what will be my VX? Actually, first of all, I want to say what is my I can define my VX. VX actually will be simply 0. Why it will be 0? Because initial potential across the capacitor was 0, and no charge transfer has taken place after this switch has been closed. So obviously this capacitor is at same state, that is 0 voltage. So obviously this whole potential is 0 and this is ground, so this Vx, right, will be simply 0 potential. So with respect to ground, this Vx is also 0 potential. What about Vax? This time Vax, what about Va? Va also is defined simply as 3V by 2. Okay, 3V by 2, simple as, right? Previously Vax was 3V by 2, but now X is also grounded, so it can be written as Va equals to 3V by 2. Okay, so this will be the answer for this second part. Now let's come to the third part. Things will become more trickier. Okay, up until now you could have used a simple charge equation, right? But now things will become trickier if you don't use this particular concept. So here I will take this. So again I will check for t less than 0. So t less than 0, again if this switch is open, this node is open, so no charge transfer will take place here, and this node is also like this point is also open, so again no charge transfer can take place here, so everything is fine, no change of states. Now at t equals to 0, the switch has been closed. So at t equals to 0, the switch has been closed. So as the switch has been closed, what will happen? As the switch has been closed, basically again some X amount of charge will flow out of this 2 volts. Now it has two paths. Either it can go to ground or it can go to this left hand side capacitor. Which one will it choose? Can it go here, right? If it goes here, it needs a return path to come back to this node, right? Because whatever charge has been left, this should come back to the other plate. Okay, but how will it come back? No path for this to come back, right? Only charge can flow like this. Complete loop is forming like this only. There are no other loops. So obviously again X amount of charge will leave and that will go here. Again the equations will be same. Okay, this equation will be ditto copycat, exact same. Okay, but okay, this Vax is again same, like because this node is X defined, right? But what is my what is my potential Vx this time? Can I define it this time? I can actually, because I have been given a reference. So this X amount of charge is this. So what is the Vax basically? What is Vax? Vax is same as the previous case, that is 3V by 2. Now interestingly, this node A, right? This is the node A, right? This node A is actually grounded. So what is my Vax can be written as Vax is equals to Va minus Vx, that is 3V by 2. So Vx is equals to minus 3V by 2. Why is that? Because with respect to this potential is minus 3V by 2, right? Because this has discharged by half voltage V by 2. Also another way, this Va is 0. So Va is 0, so Vx will be minus 3V by 2. Like that also you can understand, right? So this time my potential is defined at node X. Why is it defined? Simply because I have been given a reference point. So whenever you are solving an interview question, or whenever in the interview you have been given a circuit, always do take a note that is reference given or not. Okay, we take this for granted. Okay, just take care of this. Just be careful of this. So here let's come to the D question. Okay, if I come to the D question, what will happen? So at the D question, again I will check t less than 0. So t less than 0, can any charge transfer take place? Again, this doesn't have any loop forming because this path is open, right? This also cannot form any loop because this path is open. Now this is between two grounds, okay? Like this node is fixed to ground and this node is also fixed to ground. So obviously this is also zero potential. So this, right, this will actually remain at zero potential. Okay, this will actually remain at zero potential. Why? Because the positive plate of this capacitor is fixed to ground and the negative plate is also fixed to ground. Okay, this will not change. So this potential is always zero. So initially this potential difference was also zero and this will be zero. So my Vx, right, Vx will be 0. Anyways, you can see like this is fixed to this ground point. So anyways, this will be 0. So you don't have to do any other analysis. Okay. But what we know is, again, the same equation will be valid, that again the potential difference across this capacitor will be 3V/2 and same as this. Okay. That will happen because some X amount of charge will flow from this 2V capacitor and that will totally circulate in this loop. Okay. So this Vx will be 3V/2. Now what is next? Let's come to the E circuit. Now E circuit is the most interesting one. Okay, E circuit is the most interesting one. We'll do this. Okay, so from here your simple equations, right, those charge conservation equations, you won't be able to use those. Obviously you will be able to use those, but it will be much complicated. So here if I paste this circuit, right, so now before closing the switch, again will any closed loop form? No, right, this again will not form any closed loop because this is actually stopping me from forming the closed loop. Again, this also will not form any closed loop because again this is stopping me. So now if I close the switch, if I close the switch, so now what will happen is that actually this is forming a closed loop because these points are grounded, right? So I can actually connect this, like these are actually virtually shorted because these 2 points are grounded. Okay, and here is also another loop. So there are 2 loops now. So if I assume some charge is flowing out from here, let's say X charge is flowing out because this is higher potential, right? So this will give out some charge. Just my assumption. If my assumption is wrong, this X will come out to be negative. No worries about that. So this is giving out some charge. Now what will happen is some charge will flow here and some charge will flow here. And that charge will flow through this ground and come to this this plate of the capacitor, and other one will come to this plate of the capacitor. Then they will actually meet here, and then again it will be X. So what do we mean? So let's assume that the charge on this path, right, is actually Y. Okay, and on this path is actually what will be the charge here? So if X charge is totally coming out and Y charge I have already given to the left hand side, so the remaining charge will come here. Simple KCL. Okay, so it will be X minus Y. Here how much charge is coming in? Actually X minus Y. And how much charge will leave here actually? So if this plate, right, is X minus Y, this plate will be minus X plus Y. Just the opposite, right? Because overall charge, summation of overall charge on the 2 plates of the capacitor should be 0. Now here Y charge is incoming, so this is plus Y, and here that means minus Y charge will leave. Okay, and again here if you observe that the sum of charge, right, here Y is there, here X minus Y, so total X I get back here again. So these are the equations. So what I will do, I will again this time I will write my potential at this node Vx directly because I haven't given this ground reference points. So I will write the voltage Vx here. So how will I write? If you are not able to understand how am I writing this, I highly recommend to go back and watch the part 1 of this switch capacitor series. So Vx is equals to what? Vx equals to this charge, right? Basically what is the charge at this plate? The charge at this plate is this is minus CV minus Y. So charge at this plate is minus CV minus Y and divided by the capacitance, that will give me the voltage. Overall charge divided by the capacitance gives me the voltage. This should be equals to, because this, right, this has been finished here, because if I find this potential across this capacitor, this is actually with respect to ground, so that work is finished. Again through this capacitor if I find the potential, what will be this? So this actually this node is minus 2 CV, and this from here, right, I'm giving out X charge, so this is minus X because I'm giving out the charge, and this should be plus x because charge is entering, coming back here, right? Charge is again entering here. Although I can also say the summation of the charge on the two plates should be 0. So here, what will be the potential? The potential here will be x minus 2CV divided by C. Okay. Now let's come to the third equation. Third equation is here. And why do I need 3 equations? That also I will say. No, not 3. We have 2 equations. That also I will say. So this potential, right? This potential will be what? Here I have minus x of charge and plus y. I didn't have any initial charge. So this will be minus x plus y divided by C. So once I will equate with this equation, and once I will equate with this equation, okay? And if I do that, right, I will basically get back my x and y values, and through the x and y values I will be able to compute my Vx. So if I do one thing, if I equate these two, right, if I equate these two, what will I get? So here I will basically get, now why am I writing C here? Because next time, right, if this C becomes C by 2 or 2C, that's why all this will change then. Okay, so that is the interesting part, that is the homework for you. So here this will become x plus y, and on that side it will be CV basically. And my, what is my x minus y basically? So I can say from here, right, this will be 2x, like I have equated these two, and now I will equate these two. So this will be 2x and minus y equals to 2CV. Now if I simply add these two, right, what will I get? If I add these two, x will be equals to CV. Okay, x is equals to CV. Okay, if I add these two, this will be CV, yeah, fine. And what will be my y equals to? Y equals to, right? Okay, if x is CV, y is simply 0. Okay, y is simply 0. So there is no charge transfer taking place. So that is one thing. So now what will happen? Now I can find out my potential x. So what is my potential x? Like either way, you can find out from this equation, from this equation, from this equation. Any equation you like, you can find out. So the easier one is here, because if I put y equals to 0 here, my Vx will come out to be minus CV by C, that is minus V. Okay, so my Vx will be actually minus V. So what is actually happening is that this, right, this capacitor is actually giving out V, like what is the delta V of this? V simply. So this capacitor is actually giving CV amount of charge, and all of the charge is actually going to this capacitor. Okay, and none of the charge is actually going to this capacitor. So that is the interesting fact here. None of the charge is actually going to this capacitor. Why? Because y is equals to 0. So this remains at the same state plus V voltage, which has been proved from here as well, minus Vx. But this actually changes the state of this capacitor. So this is very interesting fact. So my Vx is minus V, and you can analyze the voltage potentials of all the other nodes. Okay, all these things you can analyze. Let's move on to the next question, next circuit. So I will copy the circuit F basically. So just hold on, I will copy the circuit F. This is circuit F. So here again, t less than 0, right? Is there any charge transfer? Actually, interestingly, this, right, is forming a loop, because this is also grounded, this is also grounded. So these are actually same points. These are actually same points. These are actually same points. Okay. So if these are same points, what will happen here? So basically this will form a closed loop. So before even closing the switch, if I place a capacitor here, right, at these 2 points, what will happen? This capacitor will actually discharge through this capacitor, and again it will come to some steady state. Okay, it will come to some steady state. Then what will happen is that this point, right, will actually become grounded. Okay, this point, this A point will become grounded, and this point was anyways grounded. So at the end state, right, at the final state, actually Vx will be minus V only. We'll cross verify this, but take my word, Vx will be minus V. Just the charge transfers will differ, because initially this has been reduced from V to some other potential, that we'll see. Okay, so that thing will only change, except that the final state, right, Vx will remain minus V. That I will prove. So first of all, I will start for the case t less than 0. What is the potential across the capacitors? So for t less than 0, this switch, right, is actually basically open. So if this switch is open, basically I can use the same formula. So again, I will compute the voltage at this node Vx. So Vx for 0 minus. What will happen? 0 minus. So 0 minus basically this, right? This will actually give out some charge to this capacitor because there is no path for charge to flow here. So basically some X amount of charge will leave and will come here because they are actually connected. And here, right, this will be minus X and this will be plus X because here X is incoming and here X is outgoing. Here again X is outgoing, so this will be minus X and this will be plus X. Okay, so what will happen? Basically here I can write it like this. For this particular capacitor, right, this will be minus X by C equals to, here, right, I have minus CV. Already initial charge was minus CV and I have to add plus X. So minus CV plus X by C. I have only one unknown variable, so I have only one equation. So CC will get cancelled and my X will become CV by 2. So basically my this Vx, right, what will be Vx? Vx will be minus X by 2. So Vx 0 minus will be minus CV by 2 by C. So this will be minus V by 2. Minus V by 2. Okay, so this voltage will be simply minus V by 2 before T less than 0. Now after T less than 0, how can I draw the circuit? So everything will change after T greater than 0. So not less than, greater than 0. So again I will not mark out the charges now. I will just make them like, I will mark out the new charges. New charge transfer will happen, right? So this potential will actually become V by 2. And this potential also like this becomes V by 2, right? So with respect to X, now my potential is minus V by 2 and these points are actually connected. Now again some charge transfer will happen because this is the higher potential. So this actually will give out some charge. Let's again assume it as X dash, right? So this gives out some charge X dash. So some of the charge can like come from here and come back to here, and other charge can actually follow this loop. So let's assume Y charge goes into this C capacitor, and here how much charge will go out? This will be X minus Y. So again this is connected actually. Okay, again here how much charge is coming? X minus Y. So at this top node of the plate of this capacitor, how much charge I have? Minus X plus Y, just equating it with 0. So what will happen? And at this node, right, at this plate, how much charge do I have? Here Y is incoming, so this is plus Y. So this will be minus Y basically, and already I have minus Vc by 2 potential here, and this is minus X dash. Let me name everything as dash, else there will be a bit of confusion. Dash dash. So this will be basically minus, not minus, plus X dash, because why? Because here X is leaving, so this is minus X dash, this will be plus X dash, and already I have minus 2 Vc. So I will again write the equation of the voltage at node X greater than 0. Okay, greater than 0. So this will be Vx 0 plus. So Vx 0 plus will be what? Vx 0 plus will be, I can write either of these equations. So first I will write this equation. This will be minus X dash plus Y dash divided by C. Also don't forget initial voltage. This time this capacitor has initial voltage, so this will be minus CV by 2 should be equals to this potential. So what is this potential? This is minus CV by 2 minus Y dash minus CV by 2 minus Y dash divided by C. So here again what will be the potential through this capacitor? So this is right, this actually will be minus 2 Vc plus X dash, minus 2 Vc plus X dash divided by C. So now I can compute the X dash and Y dash unknowns variables. So what I can do is I can solve this. So here Cc will get cancelled and here if y goes there and 2vc goes there. So x dash plus y dash will be equals to 3vc by 2. And here what will happen? Basically, this, right, I can again equate this. So if this y dash goes here, this is 2y dash minus x dash will be equals to 2y dash minus x dash will be equals to this cv by 2 actually cancels out, so this will be equals to 0. So basically my x dash equals to 2y dash. So if I put the same value here, right, so this will be y dash will be equals to vc by 2. So if y dash is equals to vc by 2, so another vc by 2 is coming. Again, this will come back to its v potential, okay, just previously. So my vx, my x dash will be vc, so my vx will be v only, okay, because this is getting charged by v by 2 again, so this will be again v by 2 plus v by 2, so that will be v. And from here also I can observe that, because this will be what, x equals to vc, okay, so x is equals to vc, this is getting charged here on this node vc, and I have subtracting vc by 2, so overall this is getting charged in this direction vc by 2, so that is correct. Another v by 2, this is getting charged, so again this will also become v, and this also will become v, because here x is leaving out and x is vc basically, so v potential is coming out. So I come back to the same state just like the previous example. So vx will be minus v only, because here also this node was grounded and here also this node is grounded only, because this is shorted. Just the difference is initially there will be some charge transfer between these capacitors, but finally overall the potential will be same, because overall only I have these three capacitors and no energy like dissipating element is present. So obviously at the end, right, the potential will be same, even though the reference were different, okay, but as these 2 points were actually same at the steady state, so that's why the potential also becomes same as minus v. So vx will be, so this will be not plus v, this will be minus v. So this will be an answer to this question. So the homework for you is this one. This one is also very interesting. Try to solve this and let me know in the comments below what will happen. And obviously don't forget to check out our courses at prefusion.in. You can get comprehensive like classes, all the recorded classes are present, and obviously you can join our doubt clearing group. There are almost 300 students, like in various doubt clearing groups, almost 300 students are there. We discuss all their regular doubts and their preparation doubts as well regarding gate preparation and all. So yeah, thank you for watching, and I will see you in the next lecture.